Hello, I'm Tom.
And I'm Mia.
Welcome to the Adaptix podcast. You know, this is our series where we turn these really advanced ideas in artificial intelligence and robotics into, well, simple, clear explanations. I mean, we all know this field moves so fast, and a lot of the time it can feel pretty overwhelming. So our goal is just to create a space where anyone, and we mean anyone, can build their understanding at their own pace. Doesn't matter if you're just getting started or maybe you're exploring the broader world of intelligent systems. Let's dive in.
In this episode, we want to explore 4 of the most influential neural network families: convolutional networks, recurrent networks, autoencoders, and generative adversarial networks, and understand what they're designed to do and why they matter. Welcome. For anyone looking into modern artificial intelligence, the landscape can feel, well, a little overwhelming. It seems like a new groundbreaking model appears every week.
It really does. But when you look past all the different names and, the marketing terms, you start to see a pattern.
You realize that most of the foundational breakthroughs in modern machine learning stem from just a handful of fundamental architectural families.
Exactly. We're talking about CNNs, RNNs, autoencoders, and generative adversarial networks.
Right. The big 4.
That's the perfect framing. If deep learning is a building, these 4 families are really the foundational pillars. And the reason we need this variety comes down to the data itself.
Data isn't just one thing.
Not at all. You have images, which are all about spatial relationships. You have text or speech, which are sequential, they happen over time. And then you have completely different challenges, like how do you compress data or how do you generate something new?
So you can't just have one size fits all.
You can't. An effective deep learning architecture has to be tailored to the inherent structure of the data it's trying to process. So today, our mission is to explore the specific why behind each of these core innovations and really highlight the critical problems they solved.
Okay, so let's unpack this, starting where the revolution, for many people, really took off. Convolutional neural networks, or CNNs, before they came along, just processing an image with deep learning was, well, it was deeply inefficient.
It was an incredible bottleneck. I mean, the standard network back then was the multi-layer perceptron, or MLP, and it just treats every single input feature independently.
So every pixel in an image is just another number with no connection to the pixels next to it.
Exactly. Imagine trying to feed a moderately sized image, say a 200 by 200 pixel color photo, into one of these MLPs.
Okay, that's 40,000 pixels times 3 for the color channels. So 120,000 input features.
Right. And if your first hidden layer has the same number of neurons, you're suddenly looking at billions of connection weights just between those first 2 layers.
Billions. That's computationally impossible to train.
It's prohibitive. But even more importantly, the MLP fundamentally ignores the most critical thing about vision. Information in an image is local.
The color of a pixel right in the center of my screen is strongly related to the pixels immediately around it, not some random pixel way over on the far edge.
Precisely. The core architecture was just fundamentally flawed for visual data.
So where did the idea for a better approach come from?
Well, as it so often does in deep learning, the breakthrough came from biology. It's based on the Nobel Prize-winning work of neuroscientists David Hubel and Torsten Wiesel.
The ones who studied the visual cortex of cats, right?
That's them. They found that individual neurons in the cat's visual cortex weren't looking at the whole scene at once. Instead, they were specialized.
How so?
Each neuron was only sensitive to visual stimuli within a very small, specific area. They called it the neuron's receptive field. And these neurons often specialized in simple patterns, like detecting a horizontal line or a diagonal edge or a little patch of light.
And that's the spark for the convolutional neural network, the idea that we should build networks that act like that, looking at small local regions to find local patterns.
Exactly. And this leads to the fundamental operation, convolution. Think of it not as a magnifying glass looking at the whole image, but as a small, highly specialized window. We call it a kernel or a filter.
And this little window just slides across the entire input image.
It slides across, and at each position, over a little patch of pixels, it performs a specific mathematical operation to extract a local feature, an edge, a corner, maybe a bit of texture.
And the output of that whole sliding process is what we call a feature map. But what's the trick that makes this so much more efficient than that MLP nightmare we talked about?
This is the sheer brilliance of it. It's an idea called weight sharing. Imagine you design a small, say, 3x3 kernel that's perfectly tuned to detect a vertical edge.
Yeah.
In an MLP, you would have to learn a brand new set of weights for every single location in the image where a vertical edge might appear. But in a CNN,
You just reuse the same one?
you use that exact same kernel, the same 9 weights, and you apply it across the entire input image everywhere.
So instead of learning millions of unique connections, we learn just 9 weights and we reuse them. That is an astonishing reduction in complexity.
It's the defining feature of CNNs. It just drastically cuts the number of trainable parameters. A famous early example, Latent 5, was designed for handwritten digit recognition. It had over 345,000 connections, but thanks to weight sharing, it only needed about 60,000 trainable parameters.
And beyond just being efficient, this reuse gives the CNN a really crucial property, doesn't it? Something called translation invariance.
Yes, because if your vertical edge detector is useful in the top left corner of the image, the fact that you're sharing those weights means the network automatically knows it's also useful in the bottom right or in the center.
The feature can be detected no matter where it is.
Exactly, and that's vital. If you're looking for a cat's nose, its exact pixel coordinates shouldn't matter. The network should recognize the nose feature wherever it happens to appear in the picture.
But what if the image is slightly distorted? Or, a handwritten number is a little bit rotated or shifted over? Pure convolution might still have some trouble with that.
It could, and that's where the second key component comes in, the pooling layer.
So convolution extracts the features.
And the pooling layer is what gives it true shift invariance.
Yeah.
Its main job is really dimensionality reduction. The most common type is max pooling.
Max pooling. So the network slides another window over the feature map and just takes the biggest number.
It simply takes the maximum value within that region.
Why does taking the maximum value help with shifts and distortions?
It acts as a kind of summarizer. Let's say a feature detector, maybe a corner detector, fires really strongly somewhere inside a little 2x2 region of pixels. Max pooling just records that strong firing, and it ignores the exact coordinate within that 2x2 box.
Ah, I see. So it's less sensitive to the precise location.
Right. By reducing the size of the feature map, it makes the output representation less sensitive to slight variations. Whether the digit is 1 pixel to the left or 1 pixel down, the pooled output is probably going to be the same, making the whole network more robust.
So convolution detects and pooling stabilizes and compresses. This was the recipe for success for a long, long time. But as people wanted to tackle more complex tasks, they realized they needed deeper networks. And that brought back an old demon.
The demon of optimization difficulty. Specifically, the vanishing gradient problem. This is a huge theme you'll see across all of deep learning.
It's the idea that as we make the network deeper, the signal that's supposed to help it learn just fades away, right?
Yep. Exactly. When the error signal propagates backward during training, the gradients, those are the signals telling the weights how to change, they can become exponentially small. By the time they get back to the early layers of a very deep network, those layers they essentially stop learning.
And that frustrated researchers for years. The assumption was, if you stack more layers, the network should get better. But beyond a certain depth, the performance would actually get worse.
It would degrade because those deep layers just couldn't be trained effectively. And this is why the introduction of residual networks, or ResNets, was such a profound turning point. They won the big ILS VRC 2015 competition and just changed everything.
And they did it with such an elegant, simple idea. It all centers on this identity shortcut connection. It's almost, counterintuitive how a simple line bypassing the layers changed the whole game.
The core idea is incredibly simple, but its theoretical impact is huge. So traditionally, a stack of layers is trying to learn some complex mapping. Let's call it h of x. What ResNets did was introduce a shortcut connection that adds the input, x, directly to the output of that layer stack. So now, the layers are only asked to learn the residual mapping.
The residual, so the difference.
The difference. The layers learn f of x such that the total output is h of x equals f of x plus x. So the network isn't learning the entire function from scratch anymore. It's only learning the deviation from the input.
And why is learning just the difference so much easier?
Well, think about it this way. In a standard deep network, if the best possible mapping is actually very similar to the input, what we call an identity function, the network has to work incredibly hard adjusting all these weights and all these nonlinear layers just to output something almost identical to what it started with.
Which seems really inefficient.
Very. But with the residual block, if the best function is identity, the network just has to learn to make that residual term f of x go to 0. And pushing something towards 0 is a much, much easier optimization task.
It's like it provides a free safety net. If the layers decide they can't improve the representation, they can just learn to output 0. And the identity mapping, the shortcut, takes over. It preserves the information.
And that preservation of the signal is the key. Those shortcut connections ensure the gradient signals can propagate effectively backward through hundreds of layers without vanishing. It allowed for these previously impossible depths, like 152-layer networks.
And that innovation, combined with convolution, meant that CNNs completely took over. They replaced the need for human experts to design visual features. The network just learns everything from raw pixels.
Exactly. That structural trick fundamentally changed computer vision.
It really did. But now, we need to transition. We're moving from the domain of space of images to the domain of time. We're talking about sequential data.
Right. So if CNNs are specialized for capturing spatial hierarchies, recurrent neural networks, or RNNs, are specialized for the flow of time and modeling sequences.
So why do traditional models, even very deep CNNs or MLPs, just fail so catastrophically when they're dealing with sequential data? You know, things like text or spoken language.
Because they have no memory. Sequential data is dynamic. The meaning of the current word in a sentence or the current sound in a speech signal is entirely dependent on what came before it.
And a standard network needs a fixed size input. It can't look back in time.
It can't. It has no way of capturing those temporal dependencies unless you give it some huge predefined history window, which is just impossible in practice.
And that's the problem that RNNs were designed to solve by introducing this recurring element.
Yes. The core mechanism is a loop, a recurrent computation of a hidden state. When an RNN processes the current input at time t, it doesn't only use that input, it also combines it with the previous hidden state from time t-1.
So that hidden state is the memory. It carries the context forward.
It acts as a unit of short-term memory, carrying all the information and context learned from the preceding time steps forward into the current moment. The output at time t is a function of the current input and all the accumulated context from the past.
It's an elegant idea, conceptually simple.
Conceptually simple, yes, but practically limited, especially in its classic form, because we immediately run into our old friend again.
The vanishing gradient problem.
But it's even more severe here.
Because the error doesn't just have to propagate back through layers of a network, it has to propagate back through every single time step in the sequence.
Correct. If you have a sentence that's 100 words long, the gradient has to pass through 100 steps. And as it flows backward through time, those signals just shrink exponentially.
What does that mean in practice?
The practical consequence is that classic RNNs could only capture very short-term dependencies. They would essentially forget information from the beginning of a long sequence. The network's memory unit was just too leaky.
So if I start a sentence by saying, the scientist who lives near the mountains and specializes in astrophysics gave a lecture. By the time the RNN gets to the verb gave, it might have forgotten that the subject was scientist.
Precisely. That long-term dependency would just vanish. And to fix this, researchers needed a way to control the flow of information much more precisely. This led to the revolutionary development of long short-term memory networks.
LSTMs. They're a perfect example of architectural innovation solving a fundamental theoretical problem. Instead of just one leaky memory unit, they use this sophisticated system of gates.
The gates are the genius of LSTMs. They introduce this structure that allows the network to selectively retain or discard information. It can maintain context over hundreds, even thousands of time steps.
How does it work?
An LSTM unit has a distinct cell state, which you can think of as the long-term memory conveyor belt. It runs straight through the unit. And the cell state is regulated by three main gates, which are essentially small neural networks themselves.
Okay, so what are the jobs of these individual gates?
Well, we start with the forget gate. And its job is exactly what its name implies. It looks at the current input and the previous hidden state and decides which information in that cell state is no longer relevant and should be forgotten.
So it prunes old, unhelpful context.
Right. Then you have the input gate, which does the opposite. It decides which new pieces of information from the current input are important enough to be added to the cell state.
So forget gate prunes, input gate adds. They work together to update the long-term memory.
Exactly. And finally, you have the output gate. It looks at the current updated cell state and decides what portion of that total memory should be exposed or outputted as the new hidden state for the next time step.
That selectivity is what gives them their power. They can actually control the flow of information.
And that's what ensures important context doesn't just vanish over time.
Now, LSTMs sound incredibly effective, but they also sound heavy. They have to manage all these interacting components at every single time step. Did we ever find a way to simplify that structure without losing all that power?
We did. And that's where gated recurrent units, or GRUs, came in. They're a highly efficient alternative.
How do they simplify things?
The architecture combines the forget and input gates of the LSTM into a single update gate. And they also merge the cell state and the hidden state into one single state vector.
So by having fewer internal mechanisms, they have fewer parameters, which usually means they train faster.
Yes. GRUs are computationally more efficient, and they often achieve performance that's comparable to LSTMs in many-sequence tasks, especially when your datasets aren't massive. It's a smart trade-off between complexity and efficiency, which is a constant balancing act in this field.
So LSTMs and GRUs primarily capture past context. But in some tasks, like translation or maybe even prediction, sometimes you need to know the future to really interpret the present.
That's a great point, and it led to the development of bidirectional RNNs and LSTMs.
What's the structural innovation there? Is it complex?
Not really. It's simply running two separate sequence networks. One reads the sequence forward, from past to present, and the other one reads it backward, from future to present. Then their outputs are combined.
That seems like it would be a massive benefit for language processing.
It is. If you're analyzing the word bank in the middle of a sentence, its meaning changes completely if the sentence ends with "of the river" versus "of the investment firm."
A standard forward-only RNN would just have to guess.
It would. But a bidirectional RNN captures context from both corrections, which hugely enhances comprehension for tasks like speech recognition and sophisticated natural language processing. The ability of these RNN families to handle sequences made them absolutely indispensable for years.
So we've covered supervised learning for structured data, CNNs for space, RNNs for time. Now we need to shift gears a bit to a different kind of learning altogether, representation learning. The goal isn't just classification, but simply understanding the essence of the data. And this brings us to autoencoders.
Autoencoders are all about learning efficient representations, and they do it in an unsupervised way. They pose the question, can a network learn the underlying essential features of data without being told what those features are?
Okay, so what does the structure look like and how is it trained?
It's a network that's designed to reproduce its own input. It has two symmetric halves. First, you have the encoder, which takes your input data, say an image, and compresses it down into a much smaller representation.
The bottleneck.
The bottleneck, or the latent space. Then the second half, the decoder, takes that compressed representation and tries to reconstruct the original image perfectly.
And the network is trained just by minimizing the difference between the original input and the final reconstruction.
Exactly. So the magic, the real learning, isn't in the output. It's in that structural constraint, the bottleneck.
Because that middle layer is so much smaller than the input and output layers, it forces the network to distill the input down. It has to learn only the most important salient features needed for an accurate reconstruction.
Precisely. It can't just pass the input through, and it can't just memorize it. It has to figure out the most efficient compressed way to represent the data's core information.
This sounds conceptually a lot like creating a highly efficient zip file. You squeeze all the vital information into a tiny package, but you retain just enough to fully restore the original quality.
That is an excellent analogy. What the autoencoder is discovering is the underlying manifold of the data. There's this hypothesis that high-dimensional data, like images, actually lie on a much lower-dimensional hidden structure. The autoencoder's job is to learn that compressed structure.
And what happens if the input data is messy or noisy?
That leads to some really powerful variants, like the denoising autoencoder. In this case, we deliberately feed the network a corrupted version of an image, maybe one with random noise added, but we task the decoder with reconstructing the clean original image.
So it has to learn to see through the noise.
It learns to ignore the statistical noise and focus only on the true underlying signal of the data. It makes the final representation much more robust.
Now, I see the term variational autoencoders, or VAEs, mentioned a lot. That seems to be a more modern approach. How do they differ from that standard compression reconstruction model?
VAEs introduce a probabilistic twist. A standard autoencoder maps an input to a single deterministic point in that latent space. A VAE maps the input to a probability distribution within that latent space.
Hold on, why does introducing probability matter? What does that get you?
It's all about generation. If you want to use that latent space to generate new, meaningful data, you need that space to be smooth and continuous. In a standard autoencoder, if you take two valid points in its latent space and try to interpolate between them, the space in between might just be complete nonsense. It would decode into gibberish.
So the VAE needs some kind of mathematical constraint to make sure the latent space behaves predictably.
Exactly. And this is where its objective function comes in, which includes something called the Kullback-Leibler divergence, or KLD.
Okay, that sounds like some serious statistics. What practical problem is KLD actually solving here?
In this context, KLD is a regularization term. It forces the learned probability distribution in the latent space to conform closely to a desirable, simple prior distribution, like a standard bell curve.
And why do we need that constraint?
It ensures smoothness. By forcing the latent representations to overlap and conform to this standard shape, you guarantee that if you pick any two random points in that latent space, the points in between will also be meaningful.
Ah, so it makes the space navigable.
Right. This allows VAEs to be used not just for representation, but for smooth, controllable generation. You can smoothly transition from an image of one person's face to another person's face just by moving through that latent space.
That's a beautiful conceptual bridge from just compression to creative generation. Autoencoders really paved the way by teaching networks how to summarize information efficiently.
They absolutely did. And that focus on creative generation brings us to our final and maybe the most disruptive architectural family, the generative adversarial network.
Generative adversarial networks are, well, they feel like the most radical departure from traditional optimization. They move away from simply calculating errors and minimizing them, and instead they embrace game theory.
It's a fundamental paradigm shift. Instead of training one network with a predefined objective, you pit two networks against each other in this constant adversarial competition. A min-max game.
Okay, let's define the two players in this high-stakes game.
First, we have the generator, let's call it G. You can think of it as the forger or the counterfeiter. Its job is to take random noise and transform it into synthetic data, a realistic-looking image, for instance.
And then you have the opponent.
The discriminator, D. This is the detective, or the authenticity checker.
And the discriminator's only job is binary classification. It looks at a piece of data and has to decide, is this real from the training data or is this fake from the generator?
That's right. And the training is this continuous feedback loop. The discriminator is rewarded for maximizing its probability of correctly identifying both the real and the fake samples.
And at the same time,
simultaneously, the generator is rewarded for producing samples that fool the discriminator. It's trying to minimize the discriminator's ability to tell them apart.
so the forger constantly improves its fakes based on the detective's feedback, and the detective constantly sharpens its eye based on the forger's increasingly convincing fakes.
They're locked in a constant escalating arms race. The training is only complete when the generator creates data that is statistically indistinguishable from the real data distribution. At that point, the discriminator is essentially just guessing randomly. It can't tell the difference anymore.
I recall a critical technical detail here. The generator's cost function had to be adjusted early on because of some stability issues.
Yes, that was a key fix. In the very beginning, when the generator's just starting out, its outputs are terrible. They're just noise. So the discriminator can easily reject these fakes with very high confidence.
Which means the generator isn't getting a very useful signal for how to improve.
Exactly. Its objective function saturates. It's failing so badly, it doesn't know which direction to go to get better. So instead of training the generator to minimize the probability that the discriminator is right, we instead train it to maximize the probability that the discriminator is wrong.
It's a subtle change in wording.
But it's a huge change in practice. This non-saturating approach gives the poor generator a much stronger gradient signal, allowing it to escape that initial trap of bad performance and actually start learning effectively.
So how does this whole generative adversarial network approach differ, both conceptually and practically, from the autoencoder we just discussed?
The intention is different. Autoencoders are about compression, reconstruction, and learning an efficient representation of data that already exist. Generative adversarial networks are focused almost purely on synthesis and creation.
But the biggest practical difference is in how they handle uncertainty, right? The averaging problem.
That's the critical advantage. Traditional generative models often use loss functions like mean-squared error. But when the data is multimodal, meaning there are multiple plausible outcomes, MSE loss forces the model to average all those possibilities.
And averaging sharp, distinct possibilities always results in a blurry, indistinct mess.
Right. Think about predicting the next frame of a video where a 3D head is moving. The head could move slightly left or it could move slightly right. An MSE model will predict a compromise, a slightly blurred head where the features are averaged out.
But that's not realistic.
Never, because the generative adversarial network uses an adversarial loss. It trains the generator to create sharp, realistic output that fools a critic. It avoids this averaging. It learns that any realistic output has to be sharp and distinct, even if there are multiple sharp, realistic possibilities.
And this ability to create photorealistic, sharp, high-fidelity images is why they sparked the modern generative AI era. What are some of the key applications?
Well, beyond generating hyper-realistic faces that are indistinguishable from real photos, they excel at image-to-image translation. So, converting simple sketches to detailed paintings, changing the seasons in a photograph, or filling in missing parts of an image.
And then we have conditional generative adversarial networks. What does the conditional part add?
It adds control. A standard generative adversarial network just generates samples based on random noise. A CGene allows us to guide the generation using specific conditions, like class labels or text descriptions. You can tell the network generate a photorealistic image of a pink dog wearing a blue hat, and it integrates that condition into the process.
That moves it from just random creativity to controllable creativity, which is essential for any real-world tool.
And we also see the lines blurring again. There's the adversarial autoencoder, which uses this adversarial approach to regularize the latent space of an autoencoder. Even VAEs have been combined with generative adversarial networks, using the discriminator to judge the quality of the VAE's reconstruction.
So this whole journey through the four families shows incredible specialization, but also a lot of convergence. Let's step back and summarize the architectural fit. When should you use which network?
We have pretty clear domains. Convolutional neural networks are the undisputed champions of analyzing spatial structure. They excel at everything from image recognition to medical diagnostics.
And for time.
Recurrent neural networks are necessary when you have temporal or sequential structure, when you need memory and context over time, like in speech or financial forecasting.
Okay, and the unsupervised models?
Autoencoders excel at data compression and representation learning, finding the most robust, low-dimensional representation of complex data. And generative adversarial networks are built for data synthesis, creating new, complex, realistic samples by mastering the underlying data distribution through competition.
It seems pretty wry now to see a sophisticated system that uses just one of these in its pure form. They're constantly being stacked and interwoven.
Absolutely. Take video analysis. It's both spatial and temporal. So you use a CNN layer to extract rich spatial features from every individual frame, and then you feed that sequence of feature vectors into an RNN or an LSTM to capture the motion and dynamics between the frames.
The best of both worlds.
Right. We also see systems like convolutional recurrent neural networks used in speech, where convolution helps capture local spectral features before the recurrence models the temporal flow.
So the architectural innovation is about recognizing which component solves which specific problem best and then stitching them together.
It's a profound shift. Reflecting on all these breakthroughs, weight sharing, the gating mechanisms, the residual shortcut, the adversarial loss, they all fundamentally solve a theoretical limitation that was halting progress. They weren't just about faster computers. They were about finding a clever structural trick that made the whole optimization problem tractable.
It moved us away from the era where human engineers had to manually craft features, like designing a specific filter to find an edge in a photo,
to an era where the network learns those complex, relevant features directly and automatically from the data. That's the core story of these four families.
It really is.
And as we reflect on this progression, consider one final thought, tying back to the success of RNNs. The innovation that allowed us to build 150-layer networks was a parameter-free, data-independent structural shortcut, simply adding the input back to the output.
Just a simple addition.
A simple addition. This suggests that the next major breakthrough in deep learning might not necessarily be some complex new mathematical function that requires immense computing power. It might just be another deceptively simple architectural modification, a structural trick that once again makes this incredibly complex optimization landscape just a little bit easier to navigate.
A simple change that alters the course of artificial intelligence. That's a powerful idea to mull over. Thank you for guiding us through the foundational architectures that really do underpin modern AI. Thanks for listening to the Adaptix podcast. If you have any questions, feel free to reach out to us.